Welcome, everyone. Let's just dive right into this explainer. Today, we're tracing the incredible and honestly sometimes surprisingly dangerous path of electricity in modern entertainment venues. We're going to follow the power, starting from those massive overhead lighting grids hanging above a theater stage, all the way down into the isolated, tightly controlled environment of a digital planetarium projection booth. It's a journey through physics, engineering, and some very specific codes that keep the show running and, keep the audience safe.
It really brings up a fundamental question. Think about it. When you sit in a modern theater, you are surrounded by an absolutely massive electrical load. We're talking hundreds of high-wattage lights, incredibly powerful laser projectors, massive audio amplifiers, and they're all running at the exact same time. So, considering the sheer volume of power flowing through the building, why doesn't the electrical infrastructure simply overheat, melt down, and catch fire? What mathematical reality is actually keeping the building safe?
To give you a real sense of scale, just imagine the density of a backstage lighting rig. It's wild. You've got all these fixtures tightly clustered together. This isn't just a few extra lamps in a living room, right? This is a highly concentrated, dynamic electrical environment. This grid operates on a completely different level than the standard wiring you're probably used to seeing. The demands placed on these cables are immense, and the codes governing them have to be incredibly specialized to handle it.
Honestly, comparing standard residential systems to these commercial entertainment setups is kind of like comparing a bicycle to a freight train. In your house, you've got your standard 120 or 240-volt Romex wire sitting inside basic plastic boxes, managing very predictable loads. But in a theater, we're dealing with high voltages, like 480-volt delta systems. They're running through rigid steel conduit and terminating in heavy-duty welded enclosures. And more importantly, the loads aren't just a couple of lamps. They're highly dynamic, nonlinear systems that require some pretty extensive harmonic planning.
Section 1. The Hidden Diversity Rule. NEC Table 520.44.
Now, there's a specific UL listing warning you'll find on a lot of this gear. It reads, risk of fire, must be operated with a load diversity factor of 50% minimum. That blank space is usually filled with the word border light or connector strip, and this points to a hidden rule buried right in NEC Table 520.44. See, because theaters use so many cables tightly bundled together, the code allows for a more generous ampacity adjustment, a 60% allowance to be exact. But it secretly demands a massive trade-off. It legally requires that you only turn on half the circuits at any given time, or at least ensure the total load never exceeds 50% capacity. You literally cannot run everything at 100% simultaneously without risking a fire.
So you might be wondering, if lighting designers don't always know about this hidden rule, why haven't theater cables been melting down for decades? Well, it basically comes down to historical luck. If you look at survey data of theatrical dimmer loads, you'll see that 17% of dimmers historically had no load at all, and a whopping 60% were loaded to under half their capacity. Because traditional tungsten halogen lights have a low duty cycle, meaning they're turned off or dimmed down most of the time, the industry has had this built-in safety buffer that organically kept our actual usage well under that 50% diversity limit.
Section 2. Taming projector loads, nonlinear demands.
Down in the projection room, we encounter an entirely different electrical beast. Modern commercial digital and laser projectors don't draw power in a smooth, continuous wave like an old-school light bulb. Because they use solid-state switch-mode power supplies, they sip power in these harsh, highly non-sinusoidal pulses. This creates what's called Total Harmonic Distortion, or THD. Essentially, the equipment is injecting high-frequency electrical noise right back into the building's power grid.
The really crucial point here is how these harmonics behave, specifically what we call triplet harmonics. Those are odd multiples of the third harmonic, like 180 Hz or 540 Hz. In a normal three-phase electrical system, balanced currents beautifully cancel each other out on the neutral wire. But triplet harmonics, they do the exact opposite. They actually sum constructively, in phase, on the neutral conductor. This means your neutral wire could severely overheat even if the main power lines are perfectly balanced. That's exactly why NEC code strictly prohibits reducing the size of the neutral wire here. In fact, neutrals for these systems often have to be double-sized or run completely independently.
Because of all this harmonic punishment, standard dry-type distribution transformers just won't cut it. They suffer from severe eddy current losses, which means the high-frequency noise literally cooks the transformer from the inside out. Not good. To solve this, engineers have to install K-factor rated transformers, like a K13 or K20. These beasts are built with electrostatic shielding, heavier secondary conductors, and modified core geometries that are specifically designed to withstand that intense, high-frequency heating without thermal degradation.
And the electrical engineering definitely doesn't stop at the power supply. High-output laser projectors require massive HVAC systems just to keep the diodes from failing. We're talking dedicated cooling branch circuits sized to 125% of the rated load amps. Plus, strict mechanical interlocks are totally mandatory. You'll find an inline differential pressure switch sitting right inside the exhaust duct. This means the projector is physically locked out. It absolutely cannot fire unless it detects the exhaust fan is actively blowing air. And if that fan uses a variable frequency drive, you have to install line reactors to shield the sensitive projection power feeds from the fan switching noise.
Section 3. Silencing the ground loop. Audiovisual fidelity.
In premium spaces, like planetarium domes, inadequate grounding isn't just a minor annoyance, it's a critical failure. Have you ever heard that annoying buzz in a speaker? That's a ground loop. And they don't just cause severe audio hum, they can physically distort laser images on the dome screen, which instantly shatters the whole immersive experience. When you're trying to create a transportive environment, dirty power and grounding noise are just entirely unacceptable.
To fix this, engineers use a beautifully elegant piece of equipment, the balanced toroidal isolation transformer. The math behind it is brilliant but simple. First, it takes the standard 120-volt output. Second, it uses a center-tapped winding connected to ground to split that into two 60-volt conductors. And third, it runs those two 60-volt streams exactly 180 degrees out of phase with each other. Because they are perfectly opposite, any common mode noise present on the line is symmetrically canceled out right at the ground junction. It mathematically deletes the hum. It's like magic, but it's just great engineering.
But here's the catch. Creating clean power isn't enough if you don't deliver it cleanly. That's why theaters utilize isolated ground, or IG receptacles. Normally, the green ground wire is bonded to the metal junction box and the structural conduit, but an IG receptacle completely isolates the ground terminal from the metal box. It routes a dedicated, insulated grounding conductor all the way back to the isolation transformer. This keeps your super-sensitive audio and video signals totally isolated from all the random structural noise and leakage currents traveling through the building's steel framework.
Section 4. Future Theatrical Power, LEDs and Harmonics.
Right now, the whole industry is undergoing a massive shift. We are rapidly replacing those historical tungsten halogen lamps with modern LED systems. Now, remember that hidden diversity safety buffer we talked about earlier, the one that saved our cables? It only existed because tungsten fixtures had a low duty cycle and rarely produced harmonics. But modern LED fixtures? They have switch mode power supplies that are energized and on all the time, even when the light isn't physically emitting anything. They introduce continuous, harmonic-rich loads to the grid, which fundamentally changes the electrical math of the entire theater.
Which leaves us with a highly provocative question. As theaters fully transition to these always-on, high-harmonic LED systems, effectively eliminating our historical safety buffer, will that hidden 50% diversity rule still be enough to protect us? Or are we going to have to completely rewrite the rulebook for modern AV engineering? It's a massive high-stakes puzzle that the industry is racing to solve. Thanks for joining me on this explainer. I hope you never look at the lights above the stage the exact same way again.